Hello. In this video, I'll be talking to you about Math 3 Unit 6, Objective 3, Mathematical Conjectures. This particular school year, 2015-2016, not every site will get through all of Unit 6. And so I want to just give you information about what this objective is so you can decide whether it's something that you want to choose to include as you select pieces of Unit 6 to cover with your class. So the idea of this lesson is to explain what a mathematical conjecture is, and even more, the main idea is that it only takes one example to prove something's false, but even lots of examples do not, pardon my bad grammar here, even lots of examples do not prove something is true. And so students will experience that as they go through this lesson. And that's going to lead us to 6.4 and 6.5, proving mathematical conjectures algebraically, which is the heart of this unit. In this particular year, I would tell you that 6.5 is the one you should probably do. 6.4 takes us to more complicated things. They're actually easier algebraically, but harder conceptually to understand. And so that's why it's first, because it's easier algebraically. But they involve proofs with even and odd numbers. And so let me first explain to you where 6.3 leaves us, and then I can show you what that is. I personally would choose to skip this one this year, given that we don't have so much time. But I would like to do at least part of 6.5, which is at the heart of this very unit. So let me give you a peek at 6.3. When you look at 6.3, what you have here, overall, when you print this out from the Google Drive, what you'll find is a set of pages which are notes. This first page and second page, and really the third page has nothing on it except for a place where you can count count spaces to fill out a chart on page 2. These three things are the classwork. And then these last two pages, which are titled 6.3 homework, are, surprise, surprise, homework. And so those two pages would be the ones I would be sending home with students, having them maybe start in class and send home with them. So let's go back and look at the beginning, and you can see kind of what is included in this. Let me move the homework aside right now. There we go. It seems to me like I'm getting a lot of glare. I don't know if that's showing up in the recording, but let me turn off the light and see if that helps. That might be a little better. I hope that's better for you to see. So at the beginning of this worksheet, there are some number sets defined just to give us words to talk about them. Most of them, even, odd, and square, I'm sure that they're familiar with square numbers and even and odd numbers. These first numbers, we'll call them counting numbers, and this last set here we'll call oblong numbers. And just for your information, why things are called like they are, square numbers, are called square numbers because you can make a square with those. 1 is a pretty boring square, but 4, it comes from a 2 by 2 square, and 9 comes from a 3 by 3 square, and so on. So oblong numbers are like that, except for they are rectangles. So for this 2, the sides will be consecutive numbers 1 by 2, has an area of 2, just like this 2 by 2 has an area of 4. For 6, it would be the next set of consecutive numbers. 2 by 3 gives us 6, and the next one would be 3 by 4 to give us an area of 12, 4 by 5, 5 by 6, 6 by 7. These are oblong numbers. When you make a shape with those two numbers as the dimensions, you get a rectangle, and it's called oblong. And there's lots of other rectangles you can get, but these particular numbers have a name for the set oblong numbers. So that's just to help us be able to talk about them. So what I would do if I was teaching this, I would go through 2 or 3 of the conjectures together and then have them talk about it with their partners and then bring them back together to discuss. Groups that finish fast, I would have working on this. Groups that are very slow might not get very much of this done on their own. And so let's just work through a few so you can see how they go. The first part says, do the following statements appear to be true or false? So we say appear because we're not proving anything in this lesson. If false, give an example to show that. So it says twice a counting number is an even number. And so we would go to the counting numbers and we would double them. Twice 1 is 2, twice 2 is 4, twice 3 is 6, and that appears to always be true. Okay, so I don't need to put an example. The sum of two consecutive even numbers is an odd number. So if I try 2 plus 4, I get 6, 4 plus 6, I get 10. Those are not odd numbers, and so I'm going to put false. Right away, my very first example, 2 plus 4 equaled 6, which is not odd. And so that would be my example. I'm done. Twice an oblong number is a square number. So here's the oblong numbers. 2 doubled is 4, 6 doubled is 12. No, even though it worked for this one, it didn't work for the next one, so this is false. This one example makes it false. 2 times 6 is 12, which is not square. The sum of two consecutive square numbers is an odd number. So you go to square and they need to know the word consecutive. That means 2 right in a row. 1 plus 4 is 5, that's odd. 4 plus 9 is 13, that's odd. 9 plus 16 is 25, that's odd. And students might begin to hypothesize about why that's coming out true. That is true, but every other square number is an odd number, and an even plus an odd gives you an odd. So they might want to talk to you about why that's true. That's fine. They're not being asked to prove it in this case, but those are the exact kind of things a mathematician thinks about when they're trying to decide whether something is true or false. And then I would give them some time to answer them, and then convince me if they say something's false by giving me a counterexample. At the bottom, it asks them to make up 3 additional conjectures. 2 appear to be false and 1 that appears to be true. It's harder to make up something that appears to be true. If the kids are really stuck on making up something that appears to be true, I would say things like evens and odds are relatively easy to make up. An even plus an even equals an even. That appears to be true. Or an even plus an odd equals an odd. Something like that. So those are good spots to work on. What happens when you multiply evens? What happens when you add evens and odds? Things like that. So they're supposed to come out and give examples. So my example would be 2 plus 8 equals 10. That's an even. So it says for each, so even the true one, give an example to support your conclusion. I think this is true. Here's an example. And maybe I said an odd number squared is even. And let's see, 3 squared equals 9. That's definitely false. This is true. And so that's how those things might look. Get 3, any 3 from your class. If somebody really wants to share another one, that's fine. Have them share another one. And then here's the heart of the lesson, right? Can one example prove to you that something's true? Why or why not? Can one example prove to you something is false? Why or why not? And so this is exactly what we're wanting them to know. No, we might have been lucky, right? But yes, because if it's false even one time, then it's false. Okay, and so that's what we're after. And here's a really good example to show that even lots of examples doesn't prove something is true. And so in this problem, they're counting the number of sections that you get when you have points on the edge of the circle and you draw all of the diagonals you can from connecting those points. And so all the chords of the circle you can when you're connecting those points. So when you have only 1 point on the circle, the number of regions you have is just 1. And when you have 2 points on the circle, this is the only line you can draw, so you get 2 regions. When you have 3 points on the circle, there's 3 different lines you can draw, and you get 1, 2, 3, 4 regions. When you have 4 points on the circle, these are all the lines you can draw. 1, 2, 3, 4, 5, 6, 7, 8. Can you guess what the students might think is true right now? I would ask them, hypothesize, what do you think 5 is going to come out to? What are you starting to observe? What do you think 5 is going to come out to? Most of the time they'll say 16 because it appears things are doubling. And so I said, well, count them. And when you count this 5, it does actually come out to 16. Sometimes there's some debate because somebody missed a section here or there. This is a tiny section people might miss. There really are 16. So now they're pretty certain that the rule is it doubles every time. Every time you add a point on the exterior of the circle, you double the number of sections number of regions that you get. And so when they count this number 6, their hypothesis is that's going to be 32. But guess what? It's 31. So this one is the spoiler. Now, 1 false means their conjecture that it's doubling every time is false. So their conjecture might be that the number doubles. If they really wanted to get to writing in algebraic, if you have a higher class, you might have them notice that this is 2 to the first, and this is 2 to the second, and this is 2 to the third, and this is 2 to the fourth. There's a 5, this was a 4, this was a 3. This one would, I guess, be 2 to the 0, and it always looks like it's 1 less than the number of points. So if this was n, this could be 2 to the n minus 1 power, but that was false. As this one example proves to us, it's false. And if you want to count 7 and 8, just to make sure that we didn't, if there's somebody arguing about the counting, there's 7 and 8, and they can count those to see that in fact the pattern of doubling does not continue. So that is what 6 is about. That's what's going to happen in class. After that, you're going to give them this homework, and what it says is now we're going to do sometimes, always, or never true. So sometimes means you could get lucky, and some things are true, some things are false. Always means every single example it's going to come out true, and never means every single example it's going to come out false. So as you read these, the sum of 3 even numbers is an even number. That one happens to always be true. When you get this, you give an example to support your answer. So always true, I could go 2 plus 4 plus 6 is 12. That's an example to support mine that it came out. But anytime you get a sometimes, for instance, this one is a sometimes, a kind of tricky sometimes, the square of a number is bigger than the original number. Most of them will think that's always true. But it says if you have a sometimes, give one example for true and one for false. So 2 squared is 4, and 4 is bigger than 2, so that was true. But if you had a fraction, like a half, 1/2 squared is 1/4, and 1/4 is not bigger than 1/2, so it's false. And so that's a sometimes true. That one's going to be hard for them to think of. You might need to give them a little hint. Think about fractions. You can always say think about negative. They might try 0 or 1. 0 or 1 is really likely. 0 squared equals 0, and 0 is not bigger than 0. Same with 1. You're probably more likely to think of those than fractions. So anyway, that's how this goes. It's nice because it reviews some geometry content. 2 lines that intersect a third line will be parallel to each other. 2 triangles with equal angles are congruent. And so if this worksheet doesn't fit in during this time before final review, this would be a nice one for us to bring back in time for SBAC review, because we can bring up a lot of old facts that they've learned and review those and just be able to discuss those, bring those back to mind. Things like the diagonals of a parallelogram are equal in length. Lots of things like that we can bring back with this. And so all they have to do is always, sometimes, and nevers, and give examples. 1 for always, 1 for never, 2 for sometimes. And that's how that worksheet goes. So, and then that will lead us into the proving conjectures true. So if you decide to use that, I wish you the best of luck. I think it's a fun day. Thank you.